In chapters 6 and 7, we're going to now look at probability distributions. And you've kind of run into this a little bit before in chapter 5. If you remember here were the rules of probability, and we had this definition for a probability model. It's a list, often in table form, of all the possible outcomes of a probability experiment and each outcome's probability. So if you recall, we had these tables here where we were checking that all the probabilities were between 0 and 1, and that the sum was 1. So we're going to kind of take that idea right here and kind of expand upon it a little bit. This is technically a discrete probability distribution right here because you can create it in table form. But it doesn't have to be in table form. You can also do them with graphs or with formulas. And then in chapter 7, we will have probability distributions that are impossible in table form because they'll be continuous. And we'll talk about that a little bit later then. First, let's talk about discrete probability distributions. And before we even get into what that means, let's think about this just a little bit. So we had a problem in chapter 5, of thinking about NBA players. So we have 3 of them go up to the line. Each one has a 77% chance of making their free throw, being successful. So we created this entire lovely tree diagram. We figured out all the different possible outcomes and their respective probabilities, and it was kind of annoying, but we did it. And that leads us to, well, it was tedious. We took a couple pages to come up with each of these probabilities and the tree and everything. And it was kind of long and involved, and we were only doing it with 3 players. But what if we want to talk about 30 players? What if we want to talk about 300 players? There's got to be an easier way to do this, and there is. And it's a formula. So wouldn't it be nice if we could just have a formula that would figure out the probabilities for us, even if there were 300 players, even if there were 400 players, the calculator would just do it. And that is going to happen. But that's section 6.2. First, we have to lay some groundwork in 6.1 with some definitions and some basic things and some not so basic things. All right, so section 6.1, we're going to talk about discrete random variables. So it takes a sensible mind to realize that we should really talk about discrete and continuous one more time. We talked about them back in chapter 3 in section 1.1. But let's remind ourselves. So a random variable is any numerical measure of the outcome of a probability experiment. So you're rolling the dice. What do they add up to? What do the numbers say when you roll the dice, etc. And a discrete random variable, which we're going to work with in chapter 6, means that you can only take on a finite number of values. There's like 5 numbers that it could be. Or if you roll a die, for example, a 6-sided die, there's 6 numbers it could be. Or it could be a countable number of values, which could be infinite, but it's countable. 1, 2, 3, 4, 5, like the number of stars in the sky, that kind of thing. Continuous, which is chapter 7, will be a random variable that can take on an infinitely many values. So realize what this means. In chapter 6, we're going to be able to use tables. In chapter 7, we will not be able to use tables. Right? We'll have to use graphs and formulas. So in chapter 6, so I'm going to make a note, this is chapter 6. This bottom one is chapter 7. Okay. And we can use tables. We can use histograms, bar charts. So we can use tables, graphs, formulas, those kinds of things. So histograms or histograms, bar charts, those will be the same. Or some formulas. Right, that'll be it. The big deal is the table thing, right? The chapter 6, you can get a table. You could create a table with all the possible values because they're finite or they're countable. In chapter 7, that will be impossible. You're going to have infinitely many values and you will not be able to use a table. You're going to have to use a curved graph, right? It won't be a histogram. It'll actually look like a graph, a curve, like you would see in an algebra class, or formulas. All right, so let's think about this. We want to roll a 20-sided die and determine the number that comes up. Well, that is very much discrete, right? There are 20 possible outcomes, 1 through 20, and that's it. There are no other options. Now, the height of an NBA player, if you remember, that's measured. And if it's measured, that's continuous. Technically, the players could be anything on a certain scale, and that scale would be your tape measure that you measure them with. If it's something you measure, that's continuous. If it could have more decimal places, if you could just have a fine enough tape measure with more and more decimal places, then you get better and better measurements of height. Same thing with weight. The weight of your student's backpack is definitely continuous, because if you could just get a better scale, you could get more decimal places of accuracy for that measurement. If you can have more and more and more and more decimal places, that's continuous. The number of songs on a smartphone, well, you either have 700 songs or 701 songs or 702 songs. So that is discrete. I don't know why that's coming up that. You can't have 2.36 of a song. So if you wanted to make a note to yourself, the time of all your songs total would be continuous, right? So if you look down at iTunes, sometimes does this, where you can see, oh, I have 1,397 songs, that's discrete, and then it has a time frame of, it would take 3 days and 2 hours and 46 minutes and 36 seconds to play, etc. That's continuous. They're giving me those finer and finer and finer measurements of time. Okay, time is continuous. The number of songs, discrete. So all the continuous ones we're going to kind of ignore in chapter 6, and we're going to go with the discrete ones because those are the ones we can work with in this chapter. Speaking of which, let's remember some rules for a discrete probability distribution, which shouldn't come as any great shock because they're the same rules that we had back in chapter 5. So first of all, what is a probability distribution? It's what I already mentioned. It's a table, a graph, or formula which provides all the possible values of the random variable and their corresponding probabilities. The graphs will generally be histograms or bar charts. You can get other kinds of graphs as well, but those ones are pretty common. And the formulas we'll talk about in section 6.2. Now, the rules for the probability distribution are the same that we learned in chapter 5, namely the sum, that's what that capital Greek sigma means, the sum of all the probabilities must be 1, and every probability must be between 0 and 1, otherwise it's not valid. So now we have to look at these probability distributions and determine whether or not they are valid. All right, so this one is a yes, I believe. I will check it because each probability, it gets a little bit annoying to write it out. So let me see, each probability is between 0 and 1, and the sum of the probabilities is so much easier with symbols. Here. There, I'm lazy. So each probability is between 0 and 1, and the sum of the probabilities is 1. I suppose if you just write those symbols, you won't know what you were talking about. So let me just say each p of x is between 0 and 1, and the sum of all p of x's is equal to 1. There we go. All right, that one's valid. What about the next one? Well, that's a lame probability distribution. It's like a weird die where you can only roll 4s. Well, nevertheless, even though it's lame, every probability is between 0 and 1, inclusive, I guess I should say, inclusive. You can have 0 and 1, that's okay, right? And the sum of all the probabilities is definitely 1. Again, it's a little bit of a strange probability distribution. I'm not sure what kind of die we would want that only rolls 4s, but, so be it. And inclusive means I can include 0 and 1. So 0 and 1 are totally valid. I just can't be any lower than 0 and I can't be any higher than 1. All right, what about C? Well, I believe that adds up to 1. Yeah, 6, 10, 11, 11 take away 0.10. But the problem is that it's a big fat no, because it is impossible for P of, technically it was P of 20 to be negative, right? Right? That's because negative probabilities are impossible. There we go. All right, what about this one? Well, we definitely have every probability between 0 and 1, so that's good. However, I think the sum on this one's a little bit not good. 2, 4, 6, 8, there's 1, 1.2. So this is a no. And then each probability is between 0 and 1, but the sum of the probabilities is 1.2. 1.2 is not good. How about this? Sum of the probabilities is not 1. It's 1.2, which is bad, right? We do not want it to add up to 1.2. We want it to add up to 1. That's what we want. As to why those are valid discrete distributions, not just valid, we explained why they were valid up here. So these two, A and B, are valid, but why are they discrete? That's because for each of them, the X value can only take on a finite number of outcomes. So it can only take on these numbers, that's it. Right? There are no other numbers and there are no infinite decimal places. So since you can only take on a finite number of values that is listed in the table, that makes them discrete, as opposed to continuous, which would be it could take on any number. So not just 1 and 2, but any number between 1 and 2, like 1.5 or 1.25, etc. And we don't have that. All right, let's move on to the probability histograms. So I said at the beginning, back here, I said that you could have probability distributions show up in a table or a graph. So far you've seen the tables on this page, and then the next page has the graphs part. So first of all, let's kind of look at this. This is the number of games in the NBA Finals, in the best of 7 series. The following table shows the number of games that have been played in every finals. So for example, it's best of 7, so 8 different times it was a sweep, right? The winning team won 4 games in a row and it's done. 15 different times the winning team won 4 games and the losing team won 1 game, and that gives you 5 total. And then so on. 6 would be 4-2, and 7 would be 4-3. They went out to the last game and had to play all 7. Okay, so we're going to construct a probability distribution of this data, of these data, I should say. So let me remind you of the total. I'm going to throw that in down here real quick. 1 second. Now, if you recall in chapter 5, we learned how to do this. You take 8 plus 15 plus 26 plus 17 and get your grand total of 66. Then to find your probabilities, you're going to divide. So you'll take 8 divided by 66, and that would be a certain value. Let me find it. 8 divided by 66, enter. 0.012. So I'm going to find all of these, and I'll be right back. There they are. I found them all. You don't really have to show the fractions, but for your notes, you want to write them both down so that way you know what you've done. And let me add these up so I can see what these add up to. 1 second. So I'm going to add 121 plus 394 plus 0.258. We'll see what we get. Oop, and it gets to 1. Yay. And again, if that became 0.999, that wouldn't, or even 1.001, that wouldn't bother us too much because we know that's just a little bit of a rounding error. And then you can see right here that I have a histogram of that same information. So for example, this first bar is happening at about 0.12